Now we are ready in this video to discuss the notion of an orthogonal complement. We'll do this eventually for an arbitrary vector space, finite or infinite dimensional, but I'd like to begin with a few motivating examples. Consider the vector space V equals R3, and let W1 be the subspace which is spanned by the vector 1, 0, 0. So this W1 is just the x-axis inside of R3. Next, I'd like to define another subspace. Well, let's define it first as a subset. Let W2 be the set of all vectors V in V such that V dot W is equal to 0 for all W in W1. Now let's remember, in R3 the dot product has this special geometric property that two non-zero vectors have a dot product of 0 if and only if those vectors are orthogonal. So we can also think of W2 as the set of vectors which are orthogonal to every vector in W1. So we can write it as this. Now W1 is just spanned by a single vector 1, 0, 0, and it's easy to see that a vector V is orthogonal to every vector in W if and only if V is orthogonal to the one basis vector in W. And so we can write this set in yet another way as follows. W2 is all V in V such that V dot, the basis vector 1, 0, 0 is 0. Any way you write it, it's easy to visualize the subset W2. First, here's W1, or at least first here's the vector which spans W1, 1, 0, 0, drawn in red down here. And so W1 is the span of this vector, so it's just the line through the origin which is parallel to this vector. So there we have a picture of all of W1. So W2 is the collection of all vectors which are perpendicular to everything along the red line, or all the vectors which are perpendicular to 1, 0, 0. And so for W2, we just get, well, essentially, I'll just draw a square to represent the entire YZ plane. You can verify that any vector in the YZ plane is perpendicular to 1, 0, 0. I've drawn a few of those vectors in green, but you can likewise imagine how any vector in the YZ plane is, of course, parallel to this one vector 1, 0, 0, and therefore also parallel to the entire x-axis. Let's next consider a slightly different example, also with V equals R3, but this time let's take a subspace which we'll call U1 to be the subspace spanned by the two vectors 1, 0, 1 and 0, 1, 1. And let U2 be the set of all vectors V in V which are perpendicular to everything in U1. That is, V dot U is equal to 0 for all U in U1. So what do these collections look like? Well, U1 in this case is the span of two linearly independent vectors. You can verify for yourself that this vector and this vector are in fact linearly independent. So the span of those two vectors gives us a two-dimensional plane inside of R3. The subspace U1 may be a little tricky to visualize. I've tried to draw the vectors in UN, I'm tried to draw the vectors 1, 0, 1 and 0, 1, 1 which span U1, these basis vectors in R3. I've tried to draw them in red down here. I hope my picture is reasonably accurate. And so U1 is just the plane that contains these two vectors. Then U2 is the set of all vectors which are perpendicular to everything in this plane. So for U2, we just get a line which is perpendicular to this plane. So there are two observations I'd like to make for each of these examples. In the first example above, W2 is not just a subset, it is in fact a subspace of V, and V is in fact equal to the direct sum W1 plus W2. Now, this claim requires some verification, which we won't do right here. I'll leave that up to you. And in my second example, U2 is in fact a subspace of V, and again V is a direct sum U1 plus U2. Both of these examples sort of went the same way. So I started out choosing a subspace W1 or U1, choosing some arbitrary subspace, and then I chose another subset, which was in a sense the collection of all vectors orthogonal to the first subspace. And in each case, I concluded that the second orthogonal set is in fact a subspace, and V can be written as a direct sum of these corresponding spaces. This is true more generally for any vector space with an inner product. So we'll state this result and we'll see some interesting examples. First, we'll set up the level of generality in which we'll state the main result. So for this result, let V be any inner product space. Remember, that just means that V is a vector space, finite or infinite dimensional, with an inner product that's a map from V cross V to R, satisfying some important conditions. Again, the canonical example to think of for an inner product is the dot product on R2 or R3, but we saw some more unusual examples in the last unit. For example, we saw a strange inner product given by an integral on the vector space of continuous real-valued functions. So we have an inner product space. Remember, the useful thing about an inner product is that in some important sets it encodes the geometry of the vector space. In particular, we have this nice relationship given by, or I should say we should have this nice definition of orthogonality, which is provided to us by the inner product. Remember, we say that two vectors v and w and v are orthogonal if their inner product is 0. And again, this all makes sense in R2 or R3 or even Rn when we have a nice geometric picture already of what orthogonality means. But the important point is that this still holds even in much more abstract vector spaces, such as, for example, the vector space of continuous real-valued functions. We can still speak about orthogonality in those very unusual vector spaces, even if we have no picture of those vectors as arrows lying in space somewhere. And now for our definition. Let W be some subspace of V. Let's fix the subspace W. Then we define the orthogonal complement of W to be the set written like this, W with a small perpendicular symbol in its exponent, often read W perp for perpendicular. The orthogonal complement is all V and V such that the inner product of V and W is 0 for every W in W. We've already seen two examples of orthogonal complements in the first, in the first two examples we saw above. W1 was the span of the single vector 1, 0, 0, and we described a subset W2, which was just the orthogonal complement of W1. And similarly, second example, U1 was the span of two vectors 1, 0, 1 and 0, 1, 1, and we described the orthogonal complement. We called it U2 at the time. Moving on, let's take an arbitrary subspace W and W in V, and let V1 and V2 be two vectors in the orthogonal complement. Then, for any vector W and W, the inner product of V1 with W is 0, and the inner product of V2 with W is also 0. And therefore, the inner product of V1 plus V2 with W can be written as the sum inner product V1W plus inner product V2W, using the fact that inner product is linear in the first and second variable. This, of course, is just 0 plus 0 or 0. And so we've shown that the set W perpendicular is closed under vector addition. Similarly, it follows that if V1 is in the orthogonal complement, that if we consider the scalar multiple RV1 and its inner product with W, this factor R factors out of the inner product, again using a property of the inner product, and then this is just R times 0 or 0. And therefore W perpendicular is also closed under scalar multiplication, and we can conclude that W orthogonal, or I'm sorry, the orthogonal complement is a subspace of V. So look, we started with a subspace W of V, and we concluded that its orthogonal complement is also a subspace of V. But there's more. Let's now suppose we have some vector little w in the intersection of the subspace W and the subspace which is the orthogonal complement of W. Since little w is in the orthogonal complement, it is orthogonal to all vectors in W, including itself. After all, we are assuming that W is in W as well. Therefore, we can conclude that the inner product of W with itself must be equal to 0, and hence, using one of the first properties that any inner product satisfies, we can conclude that W is the 0 vector. So we've shown now that the intersection of W with its orthogonal complement consists only of the 0 vector. Now, this condition may look familiar. This is one of the two conditions that a couple of subspaces have to satisfy in order to V to be the direct sum of those subspaces. So it looks like we are warming up to the possibility that V may be the direct sum of W and its orthogonal complement. But remember, two conditions have to be true in order for that to hold. Not only must the intersection of these two subspaces be 0, but we also have to have, if that's 1, we also have to have 2, that V must be the sum of these two subspaces. That is, we should be able to write any vector in V as a vector in here plus a vector in here. So we haven't shown that yet. We'll come back and show that and state the theorem, essentially that this is true, that V is the direct sum of any subspace W plus its orthogonal complement. And then we'll see a few examples.